All right, in today's lecture, we're going to finish up the second part of this section 5.4 material on triple integrals. So recall yesterday we had introduced the concept of a solid region as being described as a type 1, 2, or 3 region, depending on what types of functions are bounding our solid. And we saw that we can express these triple integrals as iterated integrals with respect to x, y, and z, x, z, and y, or z, x, y, or any of these 6 total orders that we had discussed. So in this next example that we had considered, we were asked to evaluate the triple integral of the square root of y squared plus z squared over the solid region E. So here we were told E is the solid region, which is bounded by the paraboloid x equals y squared plus z squared, so a circular paraboloid opening along the positive x-axis, and the plane x equals 9. So the plane parallel to the YZ plane, 9 units outward from along that x-axis. So as we did with our previous examples, let's start by trying to sketch our region here. So in the x, y, z space, let's see what we have here. So we said that we were considering the region bounded by a paraboloid, y squared plus z squared. So we have a circular paraboloid that is opening outward along the positive x-axis. Its cross-sections are circles, if we slice it with planes parallel to the YZ plane, and bounded by the plane x equals 9. So that would be vertical plane parallel to the YZ plane, 9 units outward from the x-axis. So that plane would slice our paraboloid in a circle. So we're talking about this solid region that lies between those two surfaces. So this is our region E. And if we were to project this solid region onto the YZ plane, we would have a disk. So let's think about our projection here. So projecting this circular paraboloid onto the YZ plane, we would have a disk. Let's call that disk D. And it's a disk of radius 3. So here, the intersection of our two surfaces, this x equals y squared plus z squared and x equals 9, gives us a circle in the plane x equals 9, defined by y squared plus z squared equals 9. So here we have the projection of our solid would be bounded on the outside by that circle. So we have that is our projection. So let's think about how to describe this solid region as a type 1, 2, or 3 region. So here we would say that E can be described as a type 3 region as the set of all points x, y, z in space such that the values for x are bounded below by the paraboloid y squared plus z squared, and above by the plane x equals 9, where our points for y and z lie in this disk, let's call it D. So here, if we wanted to evaluate our triple integral over this solid region E, of the square root of y squared plus z squared dv. We could set this up as an iterated integral, where for our inner integral, we integrate with respect to x over the range of x values. So here x was bounded below by y squared plus z squared and above by 9. The function that we were integrating was the square root of y squared plus z squared dx. And then this function that we're left with for our inner integral in terms of y and z, we would integrate over the plane region D, which was our projection onto the YZ plane. So here, this innermost integral with respect to x is the integral of a constant function with respect to x. We see x doesn't appear in our integrand, so we can think of it as a constant. And so we have the antiderivative of a constant function is given by that constant, in this case the square root of y squared plus z squared, times the length of the x interval, which was given by 9 minus the lower value y squared plus z squared. So subtracting it, we have a minus z squared. And then integrating with respect to area over that disk D. So here to evaluate this double integral that we're left with, since our region of integration D is a disk, it might be easiest to switch to polar coordinates here. So using polar coordinates in the YZ plane, we're going to let y and z be defined by r cosine theta and r sine of theta, just like we would for x and y and if we were projecting onto the xy plane. And then our double integral in terms of polar coordinates would be, well, let's describe D in terms of polar coordinates first here. So here we could think about D as the set of polar coordinates r theta such that r is bounded above by 3, since we had a disk of radius 3, and below by 0. And theta, since we're talking about the full disk, would be taken in the range from 0 to 2 pi. So our double integral that we had over the disk D of the square root of y squared plus z squared times 9 minus the quantity y squared plus z squared with respect to area can be expressed as an iterated integral in the polar coordinates, where our outer integral with respect to theta goes from 0 to 2 pi, and our inner integral with respect to r goes from 0 to 3. Now let's change our integrand to polar coordinates. So here, y squared plus z squared is r squared in polar coordinates. So taking the square root of that value, we have r. And then we're multiplying by 9 minus y squared plus z squared, which we just said is r squared in polar coordinates. And then our differential of area, dA, with respect to polar coordinates, is given by r dr d theta. So here, we notice we can make use of a little simplifying trick here. This innermost integral with respect to r is a constant. Once we evaluate this inner integral with respect to r and evaluate from 0 to 3, we see it doesn't depend on theta. So we could actually pull this integral with respect to r out in front of our integral with respect to theta, and then integrating with respect to theta, the constant function over the interval from 0 to 2 pi, well, we have the length of that interval, which is 2 pi, times our constant, that is the integral from 0 to 3 of r times 9 minus r squared times r dr. And to evaluate this last integral with respect to r, let's distribute and group like terms. So here we have 2 pi times the integral from 0 to 3 of 9r squared minus r to the 4th dr. So for our antiderivative, we have the constant 2 pi times 3r cubed minus 1/5 r to the 5th from 0 to 3. So here we're left with a constant 2 pi times, plugging in 3 for r, we have 3 cubed times 3, or 3 to the 4th, which is 81, minus 3 to the 5th, which would be 243 over 5. And then we subtract what we get when we plug in 0 for r, which is 0 here. So after a little simplifying, we're left with 324 pi over 5. All right. So let's look at some other examples. In the next part of this section, we'll describe how we can use a triple integral to calculate the volume of a solid region. So here, the following theorem says we can find volume of a region as a triple integral in the following way. So just like we could find the area of a plane region by evaluating the double integral of 1 over that plane region, we can find the volume of a solid region in space, E, by evaluating the triple integral of 1 with respect to volume over that solid region. So now that we're able to do this, let's look at an example of this. In this next problem, we are asked to find the volume of the tetrahedron, capital T, which is described as being bounded by the plane 2x plus 2y plus z equals 12, and the coordinate planes, that is the xy plane, the xz plane, and the yz plane. So let's maybe start by trying to sketch this solid tetrahedron. So it's being bounded by the coordinate planes, the xy plane, the xz plane, and the yz plane. So we'll start by drawing our coordinate axes. And then it's bounded by this other plane, 2x plus 2y plus z equals 12. And like we saw in the example earlier in this section, we can visualize the part of that plane that lies in our first quadrant by finding the x, y, and z intercepts. So to get our x-intercept, we would set y and z equal to 0, and we find x is equal to 6. To find our y-intercept, we would set x and z equal to 0, and we find y is 6. And to get our z-intercept, we set x and y equal to 0, and our equation says z is equal to 12. So not drawn to scale here, but we would have the part of that plane that lies in the first quadrant as this region here. So this tetrahedron that we're describing, that's bounded by my xy plane below, on the left by our xz plane, and on the right by this yz plane, and above by the plane whose equation is given, is shown here. We're calling this solid region T. Now we're wanting to evaluate a triple integral over this solid region. So let's think about how to describe it as type 1, 2, or 3. In this case, we can describe it as any one of those types. And my personal preference would be to describe this as a type 1 region. So let's think about the projection of this solid onto the xy plane to get some region D. So here, visualizing our projection onto the xy plane. Well, we're only working in the first quadrant. and we had a x and y intercept of 6. So we're talking about D as this triangular region, which is bounded above by the line y equals, well, it has a y-intercept of 6 and a slope of -1, so 6 minus x, where x can range from 0 up to 6. So once we have a visualization for our regions here, let's set up a description of this region, T, as a type 1 region. So in this example, capital T could be described as the set of all points x, y, z, such that our z values are bounded below by 0, that is the xy plane, and above by the plane shown here in red, that is the plane whose equation was given. So thinking about that plane as a function of x and y, we would need to solve for z. So we have 12 minus 2x minus 2y. So that's going to be our upper bound for z. And then if we took the projection of that solid onto the xy plane, let's think about the range of values for x and y. Here y is bounded below by the x-axis. So here, let me show it in a different color, bounded below by the x-axis and above by this line 6 minus x. So here, y is greater than or equal to 0, but less than or equal to 6 minus x. And our x values here could range from x equals 0, that is this vertical line on the left edge of my triangle, up to x equals 6. So here below, for sake of space, we'll say x ranges from 0 to 6. So now that we have a description of our solid tetrahedron T as a type 1 solid region, let's set up our integral for its volume. To get the volume, we would integrate over the solid region T, the constant function 1 with respect to volume. So setting this up as an iterated integral, well, our outermost integral with respect to x goes from 0 to 6. The next integral with respect to y goes from 0 to 6 minus x. And then our innermost integral with respect to z goes from 0 to 12 minus 2x minus 2y. The function we're integrating is 1. Here we ordered this in the order dz, dy, dx. So for our inner integral, we are evaluating the antiderivative of 1 with respect to z. So we have an antiderivative of z. When we plug in our upper limit of integration, we have 12 minus 2x minus 2y, and then we subtract what we get when we plug in 0 for z, which would be 0. So here we have the double integral over this plane, or over our plane region D, of the function which was describing our upper limit for that tetrahedron T. And we can see that this, of course, would give us the same result if we tried to do this double integral directly. We could think about the volume of this solid as the volume that lies above the plane region D in the xy plane, but below the plane z equals 12 minus 2x minus 2y. So this double integral that we have here is giving us that volume directly. So to evaluate this double integral, we first integrate with respect to y. So we have our first two terms, 12 minus 2x, or constant with respect to y, So our antiderivative would be that constant times y, minus the antiderivative of 2y with respect to y is y squared, where we're evaluating from 0 to 6 minus x, and then integrating with respect to x. So let's see what we have. We have the integral from 0 to 6 of 12 minus 2x times, when we plug in 6 minus x for y, we have 6 minus x minus 6 minus x quantity squared. And then we subtract what we get when we plug in 0 for y, which is 0. So here, there's a couple of ways we could go about integrating this. If we're a little bit clever, we notice that this first term, if we factor out a 2 from it, we're left with 6 minus x, and then times this second factor of 6 minus x, makes it 6 minus x squared. And then we are subtracting 6 minus x squared. So here we are left with the integral from 0 to 6 of 6 minus x quantity squared dx. And we can either integrate this by using a substitution or by expanding. So here, maybe we could expand. We've got the integral from 0 to 6 of 36 minus 12x plus x squared dx. So for our antiderivative, we have 36x minus 6x squared plus 1/3 x cubed. And we're evaluating from 0 to 6. So let's see what we're left with here. We have, when we plug in 6 for x, a 36 times 6, or 6 cubed, minus, when we plug in 6 for x here, we have minus 6 cubed, and then plus a 1/3 of 6 cubed. Subtracting what we get when we plug in 0 for x, we have 0. So these first two terms cancel. We're left with 6 cubed over 3, which leaves us with 72. All right. So we see here that we can use these triple integrals to evaluate the volumes of solid regions by evaluating the triple integral of 1 over that solid region. So let's look at another problem, sort of similar. In this next one, we are asked to find the volume of the solid, which is described as being bounded by the elliptic cylinder 4x squared plus z squared is equal to 4. So here it is a cylinder where in our equation the variable y was missing, so it's extending along the y-axis as shown in our figure. And its cross-sections are ellipses, defined by 4x squared plus z squared. So anytime that we slice this with a constant value, or a plane defined by a constant value of y, we get an elliptical cross-section. So it's being bounded by this cylinder, and it's also being bounded by the planes y equals 0. So here we see y equals 0 would be this plane shown in the back here, and then bounded by our cylinder, so still inside that cylinder, but in front of the plane y equals 0, and the plane y equals z plus 2, which is this plane shown here. It's slicing through our solid, and we can see if we slice this, we're going to get a little elliptical cross-section. So the solid region that we're talking about here, the region bounded by all of those surfaces, we'll see if I can illustrate a little more clearly. It's going to be sort of this wedge shape shown in blue. So we know to find the volume of that solid region, let's give it a name, let's maybe call this E. we would evaluate the triple integral of 1 over that solid region. So here, to get the volume, we evaluate triple integral of 1 with respect to volume over the region E, and we need to set this up as an iterated integral. So let's think about how we could describe our region E here. So this one could be described as a type 2 region. So let's think about it. Here, our region E could be thought of as the set of all points x, y, and z, such that our limits on the values of y would be these two planes. It's bounded below by the plane y equals 0 and above by the plane y equals z plus 2. So if we then project this onto our xz plane, or the plane y equals 0, we see that our projection is this disk. So here, if we were to pull this disk out in the xz plane, we have an ellipse where in the x direction we're opening 2 units. Looking at our equation here, if we set z equal, x would be 1 in this case. If z is 0, we have 4x squared is 4, so x squared is 1. So in the x direction, we're opening 1 unit. In the z direction, 2 units. So here I've shown a little not to scale. So this would be our plane region D. Here it's an elliptic plane region, so it can't be easily described using polar coordinates. Polar coordinates we can use to describe disks or circles, but since this is an ellipse, it's a little bit trickier. So let's think about how we could describe this plane region. It's given by, or the edge is given by the ellipse 4x squared plus z squared is equal to 4. So z squared is 4 minus 4x squared. So z would be given by plus or minus the square root of 4 minus 4x squared. Or z is plus or minus twice the square root of 1 minus x squared. So here the positive square root value is defining the upper half of our ellipse, and the negative square root value is describing the bottom half. So here the upper part is given by positive 2 times the square root of 1 minus x squared. Our lower boundary is negative 2 times the square root of 1 minus x squared. And our range of x values is from negative 1 to positive 1. So let's start with the limits on z. Z, we said, can range from the negative of 2 the square root of 1 minus x squared to positive 2 square root of 1 minus x squared. And our y values here can range from negative 1 to positive 1. Our x values. So to get our volume, v, let's set up this triple integral as an iterated integral. Here, we're integrating from negative 1 to 1 with respect to x. Then with respect to z, from negative twice the square root of 1 minus x squared to positive 2 square root of 1 minus x squared. And our innermost integral with respect to y goes from 0 to z plus 2. We're integrating the constant 1 in the order dy, dz, dx here. So our innermost integral, let's start with. Here we have the antiderivative of 1 with respect to y gives us y. So when we plug in our upper limit for integration, we have z plus 2 minus what we get when we plug in 0, which is 0. So we're left with just z plus 2. And then we're integrating in the order dz dx. So let's see what we have. We now have the integral from -1 to 1 of antiderivative of z is 1/2 z squared plus the antiderivative of 2 with respect to z is 2z, which we're then evaluating from the negative of twice the square root of 1 minus x squared to positive 2 square root of 1 minus x squared, and then with respect to x. So let's see what we have. Substituting our upper limit for integration in for z, we have half of the square of that value. So squaring that value gives us 4 times 1 minus x squared. So half of that is then 2 times 1 minus x squared. Then plus 2 times that twice the square root gives us 4 times the square root of 1 minus x squared. Then we subtract what we get when we plug in the negative value. So plugging in -2 square root of 1 minus x squared, squaring that value and taking half of it, leaves us with twice 1 minus x squared. We're then subtracting that quantity, since this is our lower limit of integration. And then minus the negative would give us plus, let's see where I can fit this in, plus 4 times the square root of 1 minus x squared dx. So we see that a couple of our terms cancel. This twice the square root of 1 minus x squared and minus 2, 1 minus x squared. And then our terms that we're left with, 4 times square root of 1 minus x squared and another 4, give us a total of 8 times the square root of 1 minus x squared dx. Now we can pull our constant 8 out in front, of course. We've got the integral of square root of 1 minus x squared dx from -1 to +1. So if we were to evaluate this directly by trying to find an antiderivative, we would have to make use of a trig substitution, since our integral, or our integrand, involves the square root of a difference of squares. But if we're a little clever here, we can think about this definite integral as representing the area of some region. So here, our integral that we're left with represents the area under the graph of our function, which in this case would be y equals the, or z rather, equals the square root of 1 minus x squared, which would be the upper half of a circle in the xz plane of radius 1. And then we're integrating that from -1 to +1. So we're getting the area of this half circle of radius 1. Of course, the area of half of a circle is going to be half the area of our circle, which would be pi times the radius, which is 1 squared. So we have pi over 2 for the area of the region that this represents. So here we have 8 times pi over 2, which leaves us with 4 pi for the volume of the solid region E that we're describing here. Now in the last part of this section, we can define the average value of a function of 3 variables over some solid region. And it's defined in much the same way that we define the average value of a function of two variables over a bounded plane region. So here we would say if f is an integrable function of three variables, x, y, and z, which is defined over a bounded solid region E, whose volume is given by V of E, then the average value of that function, where points are defined over that region E, is found by taking the triple integral of that function over the solid region E, and then multiplying by 1 over the volume of that region. So essentially here, this integral part, this triple integral, we're adding up the values of our function f for points x, y, z everywhere in the region E. And then we are dividing by the volume of that region, and that's how we would define this average. So as an example of this, for our last example, we are given the following information. The temperature at some point xyz in space of a solid tetrahedron E, bounded by the coordinate planes in the plane x plus y plus z equals 1, is given by a temperature function, T, of xyz, which is defined as x times y plus 8z plus 20, measured in degrees Celsius. And we're asked to find the average temperature over this solid region. So the first thing that we need to find the average value of a function over that region is the volume of that region E. And to find the volume, we need to evaluate a triple integral of the constant function 1 over that region. So let's start by visualizing it. Here, again, we're working with the tetrahedron bounded by coordinate planes. So let's start by sketching our axes so we can visualize these coordinate planes in space. That is the xy plane with the xz plane and the yz plane. In the plane x plus y plus z equals 1, which has x, y, and z intercepts of 1. So the solid tetrahedron that we're talking about is the tetrahedron shown here. We were calling it E. And if we think about this as a type 1 solid region, we could project this onto the xy plane to get a plane region D, which is a triangular region with x and y intercepts of 1. So here we have the region D. X goes from 0 to 1. Our lower bound on y is the x-axis, so y equals 0, and our upper bound is this line, which is the line 1 minus x. Slope -1, y-intercept +1. So describing this region, E, as a type 1 region, we could think of it as the set of all points x, y, z in space, where our x values, we said, go from 0 to 1, our y values from 0 to 1 minus x, and our z values are bounded below by the xy plane, which is z equals 0, and the upper bound would be the plane whose equation was given. If we solve this for z, we have 1 minus x minus y. So that would be this plane shown here as the upper bound for our tetrahedron. So 1 minus x minus y for the upper bound on z. Now to find the volume of that region, we evaluate the triple integral over that region of 1 with respect to volume. Or setting this up as an iterated integral, we have the integral where x goes from 0 to 1, y goes from 0 to 1 minus x, and z goes from 0 to 1 minus x minus y. Integrating 1 in the order dz, dy, dx. So we're left with the integral from 0 to 1 and from 0 to 1 minus x. Our innermost integral, we have an antiderivative of z, and if we evaluate at the upper limit, we have 1 minus x minus y. Subtracting what we get when we plug in 0, we have 0. And then in the order dy dx. So our next integral with respect to y, well, the first two terms, 1 minus x, are constant with respect to y. So we have 1 minus x times y minus 1/2 y squared. And we're evaluating from 0 to 1 minus x, and then integrating with respect to x. So plugging in 1 minus x for y, we have 1 minus x squared minus half of 1 minus x squared. And then subtracting what we get when we plug in 0 for y, which is again 0. So here we have the integral from 0 to 1 of what we're left with is 1/2 of 1 minus x squared dx. And we can then integrate this either by expanding or making a substitution. So here, if we were to expand this, we would have 1/2 minus x plus 1/2 x squared dx from 0 to 1. So, finding our antiderivative, we have half of x minus half of x squared plus 1 over 6x cubed from 0 to 1. So evaluating at x equals 1, we have 1/2 minus 1/2, which cancel. We're left with 1/6 minus when we plug in 0 for x, we get 0. So what we have is the volume of our solid region. So to find the average temperature, that is temp average, we would take 1 over the volume, so 1 over 1/6 gives us a constant 1/6. And then we evaluate the triple integral over e of our temperature function, which was given by xy plus 8z plus 20 with respect to volume. Now, when we found the volume of E, we had already described E as a type 1 region. So we could set up the iterated integral to evaluate this average temperature. So let's look at it here. Our temperature, our average temperature, was given by 6 times our triple integral as an iterated integral. Could be expressed as the integral from 0 to 1, from 0 to 1 minus x, and from 0 to 1 minus x minus y, where we were integrating the temperature function xy plus 8z plus 20 in the order dz, dy, dx. And then to find our average temperature, we could evaluate this resulting triple integral. Now, this particular example works out to be extremely messy when we integrate with respect to z and end up having to expand. Evaluating those last two integrals is very difficult. So here we won't go through the full work of this in the lecture. But maybe we could change our problem. Instead of finding this average temperature, let's maybe change the problem to say set up an integral for the average temperature of that region. So here we would have something like this. But I wouldn't make you go through the full detail on an exam or homework problem of evaluating such a messy triple integral.